Okay, now we're going to do some volumes again. Now that we've seen disk, we're going to look at what happens when you rotate a region around an axis and you get a hollow middle portion. And in that case, you have to use what are called washers. And so that's what we're going to do here, is look at some examples of finding volume using washers. So with all of the problems, we'll have the same set of instructions, which are find the volume of the solid obtained by rotating the given region about the given axis. Now I don't have to write these instructions for each example. So in each example, I'll give a region and I'll give an axis that will rotate it around, and then we'll find the volume of the resulting solid. So the first example, let's say the region is bounded by the curve x equals 6 minus y squared, which is a parabola that opens horizontally, and since the y squared is negative, it actually opens to the left, okay? So we want the region that's bounded by x equals 6 minus y squared, and the line x equals 2, okay? And the axis of rotation that we'll rotate about will be the y-axis. The y-axis, okay? So first things first, we might want to find any points of intersection between the curve and the line to help us with the graph. Now this one's pretty easy. You could probably do it without formally running through the process, but here I know that x is 6 minus y squared, and here I know that x is 2. So I can set those equal to one another, and I can solve for y in this case, because I know that x is the same thing as x, and one is 6 minus y squared, the other is 2. So if I solve this, I could add my y squared over here, and I could subtract my 2, and I could take the square root of both sides to see that y is plus or minus 2. So that means that these two guys intersect whenever y is 2 and when y is negative 2. So when I graph this, I know that both of these guys are going to go through the point where x is 2 and y is plus or minus 2. Okay? All right, so here we go. We're going to rotate about the y-axis, so I'll draw that here. And we're looking at the point 2, negative 2. So let's say this is 2, then this is 2, and this is negative 2. I know that the 2 points of intersection are there and there. I also know that x equals 2 is one of the boundaries of the region. So that's the line x equals 2. And then I just need to look at x equals 6 minus y squared. If I plug in 0 for y, then x is 6. So 2, there's 4, there's 6. So if y is 0, x is 6. And I already know that it goes through these points, and I know it's a horizontal parabola, so it looks something like that and continues. But when I look at the region bounded by the line and the curve, I'm just looking at this portion here. So I've got my region now. I need to rotate it around the y-axis. So what would be helpful to draw the picture here is to draw a mirror image of this region across the y-axis. So in order to do that, I need to measure 2 units to the left, right there, and that's where my vertical line is going to go, so something like this. That's the mirror image of the vertical line. And then this point here is 6 units, so I'll measure, there's 4, there's 6. So the vertex of the parabola, when I reflect it, looks something like that. And so now I have the mirror image of my region. And I need to think of it as rotating around the y-axis. It looks like a donut kind of on the outside, right? Kind of a flat donut where the inside is perfectly flat. It's not rounded like a typical donut. Now, if I want to cut a cross section of this, if I want to slice it, I have to slice perpendicular to my vertical axis of rotation. So that means I have to slice horizontally. So I might look at a slice here, for example. And if I do, then when I go to set this up, my inner radius of the corresponding washer, because the inside of this is going to be hollow, I know I'll have a washer, then the inner part of my washer is going to look something like that. The whole of the washer is going to be there. And then if I go out to my outer radius along that horizontal slice, it'll be here and here, and that will be the solid part of the washer. Okay, so we have the washer. This is hollow here, and then this is solid. Now the thickness of this washer is measured vertically, right? It's infinitely thin, but it's measured vertically, and since it's measured vertically, we call that dy. So now we have to identify the inner radius and the outer radius so we can calculate the volume of the washer, and then we have to add all of those volumes together using an integral. All right, so the inner radius is from my axis of rotation, right? From my axis of rotation out to this point. So that's my inner radius right there, that distance. My outer radius is from my axis of rotation out here to the curve. So maybe if I draw it down here, it's this. Okay, so I've got my inner radius drawn, I've got my outer radius drawn. Now if I look at my inner radius, no matter where the position of my washer is, it's always going to be the same, okay? So my inner radius here it's measured horizontally. So I'm going to take the rightmost x minus the leftmost x. And in this case, the rightmost x is the constant of 2. Minus the leftmost x is the constant of 0. That's at my axis of rotation. So it'd be x, or 2 minus 0. So my inner radius is a constant of 2. My outer radius is a little bit different. It's still measured horizontally, so it's a rightmost x minus a leftmost x. The rightmost x is right here, right? It's right here on the curve. So it changes depending on where I choose my washer. Where I slice through this solid dictates what part of the curve will be my outer radius. So this guy changes. Now, this curve, remember, is given by the equation x equals 6 minus y squared. And I know I have to integrate with respect to y because this is dy. So when I look at my rightmost x here, I have to make sure it's in terms of y. So my rightmost x here is going to be 6 minus y squared because x literally equals 6 minus y squared. Minus the leftmost x, which is measured back here to the axis of rotation, is 0. So my outer radius is 6 minus y squared. So I've got my inner radius, my outer radius. We have enough to set up the integral. I have to add all of these washer volumes together. Okay, so let's set up the integral. So to calculate the volume of a washer, I do pi times the outer radius squared minus the inner radius squared times the thickness, which here is dy. But then I need to add all of these volumes of washers together. This is the volume of that one washer. So I need to add them together, and I'm factoring the pi out, this coefficient of pi, I'm factoring out of the integral. So this infinite sum is what we're looking at. And I know that the limits of integration here have to be y values because of my dy. And so in this case, I'm going to look at going from -2 to +2. And now all that remains to set up the integral is rewriting my radii in terms of my variable of integration, y. And I've already done that over here. So this will be the same thing as pi times the integral from -2 to +2. My outer radius is 6 minus y squared. Don't forget to square that. That's what a lot of students have trouble with. you have to remember to square it. So it's certainly a good idea maybe to write this out, okay? So my outer radius squared minus my inner radius of 2 squared. And then I'm integrating that with respect to y. And so that's the setup of the integral to determine this volume. Now I want to say something that can be helpful if you notice it. When you look at the solid that's going to result, this donut-looking thing, it's perfectly symmetrical, right? The top half of this donut looks just like the bottom half. So what you can do is instead of integrating from -2 to 2, you could just do half of that integral and integrate from maybe 0 to 2. And then in the end, you can multiply the whole thing by 2 to double the volume that you get when you get just the top half. So that's a really neat trick if you notice symmetry. The reason that can be helpful is because when your lower limit of integration is 0, then it's real easy to plug in when you do the antiderivative. So I'm not actually going to do that here. I'll do it on the next example so you can see it in action, but I want to point out you can do it here too. So let's go ahead and work out the integral. All right, so the volume we get is 384 pi over 5. Now, you can see here that when we evaluated this integral from -2 to 2, if you notice this expression and this expression, they're exactly the same. If I distributed this negative, all of these signs match all of these signs. And so you can see that all of these numbers double. All of these numbers double. And so that you can see that doubling effect of the volume I talked about right here when you actually evaluate from -2 to 2. If you went from 0 to 2, you would get the same thing for this top part of the integration, the antiderivative, but then you'd have -0 because you'd be plugging 0 in. The difference would be you'd have a coefficient of 2 out here to multiply the entire volume by 2, and you would still get the same answer, okay? So don't worry, we'll show you that in the next example. All right, so there we rotated about the y-axis. In the next example, let's rotate around the x-axis. And also, we'll provide a graph for the region of the next example, just to kind of make that part a little quicker. So now let's see here. The region, we'll draw a picture of it. And we're going to rotate about the x-axis. Okay, so the region we're going to have is, in fact, let's do this. I'll put the region on the right side of the board. I'd like to draw the picture on the right side. So we're going about the x-axis, and the region now looks like this. So we're going to go on the x-axis, we're going to go from -pi/2 to +pi/2. And then on the y-axis, we're going to go up to 1. And we'll kind of draw a rectangle here. Okay? Within that rectangle, we're going to embed a curve that looks like this. And this curve is y equals the square root of the cosine of x, okay? Y equals the square root of the cosine of x. Now, what region are we going to rotate about the x-axis? If I rotated everything below the curve about the x-axis, well, everything under this curve, then I would not even need the rectangular portion, right? Furthermore, if I rotated this region around the x-axis, I would use disk because there'd be no hollowness in that rotation. So instead, the region we're going to rotate is going to be these corners. And we're going to rotate that around the x-axis. So to get started, to see our washers, we're going to draw a rough mirror image of this below. Let's use the black again. So if I do that, it's going to do something like this. And then the curved part looks something like this. And so we get the mirror image across the x-axis. Okay? So now what we can do is we can construct our washers, which will be slicing vertically since we have a horizontal axis of rotation. So I'll choose to slice right here, and I'll go up here to my inner radius. So my inner radius is from my axis of rotation to this point here, okay? Draw the hollow center of my washer. That's the hole of the washer. And then through that same vertical slice, I would slice these two outer points to get my outer radius. So my outer radius goes from the axis of rotation up to the top of the rectangle. Okay, so let's identify expressions for my inner and outer radii. I need to identify what variable I'm going to use, and that's going to be based on my dx or dy, which represents the thickness of my washer. So since my washer is vertical, my thickness is measured left and right. So it's measured in terms of x. So now let's find expressions for our radii in terms of x. So r sub o, my outer radius, is measured vertically. So it's the top y minus the bottom y, which, let's work downward here. The top y is the constant of 1, and the bottom y here is 0. Be careful not to think of this as your outer radius. You measure from here all the way to your axis of rotation, which is 0. So the outer radius is always 1 all the way across the region. The inner radius is also measured vertically, right? So we do the top y minus the bottom y as well. The top y for the inner radius is the curve y value, which is the square root of the cosine of x. And that's good because we know we need everything to be in terms of x. Minus the bottom y to the axis of rotation is still 0. So now we have both radii. We can set up our integral to calculate the total volume. So we take the volume of that one washer, which is pi, times the outer radius, 1, squared, minus the inner radius, the square root of the cosine of x, squared, times the thickness of the washer, which is dx. So that's the volume of the one washer. Then we have to add all of them together. We'll do that with an integral. And we do that based on x values from negative pi over 2 to positive pi over 2. We could totally do that like we did the last example. However, we know these cosine functions are perfectly symmetrical across the vertical axis. And so what we can do here is, instead of integrating from negative pi over 2 to pi over 2, we can forget about this left half and just go from 0 to pi over 2, right? 0 to pi over 2, that's going to give us the volume of the right half of this solid. But then we have to make sure to double it to get the volume of the whole thing. So we just move that coefficient of 2 out here to the front. So again, that's a neat little trick if you recognize it to make the integrals a bit faster. But if you don't think you're going to catch that, then work this problem from negative pi over 2 to pi over 2, and you'll get the exact same answer. All right, let's work out the integral now. And in the end, we get this volume, all in terms of pi. The volume of this solid, once it's rotated around the x-axis, ends up being pi squared minus 2 pi. Now, something kind of cool here that scared me initially when I looked at this problem was the square root of the cosine of x. That is a difficult integral. I'm not sure how to do that. However, the cool thing about using washers is you square your radius. So the square here canceled your square root, turning it into just a plain old cosine, for which we know the antiderivative. So sometimes when you look at a problem, you might look at it and say, I don't know how to do that antiderivative. Well, maybe you need to get in there, dig through the weeds a little bit, and maybe it's going to clear itself up, okay? So this is a really good example. Now, we've done an example where we worked through, we rotated around the y-axis. We did an example where we rotated about the x-axis. Now let's look at an example where we rotate around a different axis altogether. All right, so now we're going to rotate about the line y equals 1. So we're going to rotate about the line y equals 1. The region that we're looking at is bounded by, this time it's going to be bounded by 4 lines. The first one is y equals x. Then we have x equals 0, we have y equals 2, and we have y equals 4. The good news is these are all simple straight lines, and intersection points are going to be very simple here because this is about the easiest slanted line to work with. The y and the x are exactly the same. So when we go to graph this, just roughly sketching it, because we've got to get a feel for what the region is, right? The line y equals x is this diagonal line. The line x equals 0 is the same thing as the y-axis. And then we've got the line y equals 2. And we've got the line y equals 4. So we can see that when we look at all of these lines, right, the region we're looking at is this region right here. And we're going to rotate about the line y equals 1, this line here. So we're going to take this region, we're going to swing it around this horizontal line to create a solid. This thing's going to have a sharp point right here, right? When you rotate it around, it's going to have a sharp point, just to get an idea of what it looks like. Now, let's be a bit more precise, graph this better now that we understand what we're looking at. It's a trapezoid, right? It's a trapezoid. The bottom and top are parallel. The left and right sides are not parallel. Okay, so we're interested in that 2 and 4 area. So if we look at this, our axis of rotation is at y equals 1. Here's our x-axis. We're rotating around this guy. And we've got 2, 3, 4. We know that those are boundaries. So 1, 2, 3, 4. And so y equals x, so here's 2 and 4. Y equals x is going to hit the y equals 2 line at 2, 2. So there's the bottom of our trapezoid. And it's going to hit the 4 line at 4, 4, which maybe is like up here. And so there's the top of our trapezoid, and then here's the side. So the region we're looking at again is this region here. And what we're going to do is we're going to take it and swing it over this horizontal line y equals 1. So we have to draw a mirror image of our region on the other side. So I'm looking at a unit of 1 away from my axis of rotation. So I'll go 1 unit below, and I'll mirror this small side of the trapezoid right there, okay? And then I'll mirror the top side, which is 3 units away from my axis of rotation. So I'll go 1, 2, there's 3 units, and it goes out here, it's a length of 4. So I'll go 4 units to the right, like this, and that's the slanted part of my region. So now I've got a mirror image of this guy across that horizontal line, right? So now I need to construct a washer and see what happens. Now, this example is interesting in a couple different ways. First of all, we're not rotating about the x-axis or the y-axis. We have 4 lines creating our region also. The other thing that's really interesting is when I start to, for example, I need to slice this, and I need to slice it perpendicular to my axis of rotation. So I'll slice it vertically. If I slice it right here, my inner radius looks like that, okay? So my inner radius for this looks like that. It's that distance. And then my outer radius, if I keep slicing all the way through, the outer radius looks like this, okay? But then if I were to slice over here, right? Then my inner radius now looks like this. And my outer radius looks like this. So my washers are constructed differently. You should be able to see that from 0 to 2, remember that this is an x value of 2 here. From 0 to 2, my inner radius and outer radius are both dictated by the same thing all the way across. The inner radius from 0 to 2 is dictated by the top and the bottom, which are the lines. The outer radius is dictated by the line and the line on the bottom. But once you go from 2 to 4, remember this is 4, once you go from 2 to 4, the inner radius depends on the slanted line now. That's a shift from how the inner radius was calculated here. So we have to change our washer. The outer radius is still the same. So what we have to do is we have to do 2 integrals here, and we have to add the volume that's going to be obtained by the purple washers to the volume that's going to be obtained by the green washers. So this one's interesting in that respect as well. So let's set up, let's find our radii. Let's find the purple radii first. The outer radius is going to be the top y, right? The top y minus the bottom y, which is 1. So top y is 4 minus the bottom y is 1. So our outer radius is a constant of 3 across this region. Okay. Now the radius, remember, runs from here to the axis of rotation. That's why it's 3. It's not 2. We're not running from here to the bottom of the region. The inner radius is also the top y minus the bottom y, so that's 2 minus 1. So the inner radius is 1. So the cool thing about the purple washers are they have constant radii. They don't have to depend on the variable x, which is the dx is the width or the thickness of each of these washers in this particular problem. Okay? But when we go over here to the green washers, we can see that the outer radius is going to be the top y minus the bottom y. The top y is 4. It's a constant still. And the bottom y is your axis of rotation, 1. So it's still 4 minus 1, which is 3. So you've got a constant outer radius. But your inner radius now is different. The top y is dictated by a slanted line, which is the line y equals x. So the top y in terms of x is literally x, because y equals x. So the top y is x, minus the bottom y is the constant of 1. So we have all of our radii. So now we have to construct two integrals for two volumes and add those together. So what we get for the purple, let's do the purple washers first. For the purple washers, we have pi times the outer radius, 3 squared, minus the inner radius, 1 squared, right? So pi times outer radius squared minus inner radius squared times the thickness, which is dx. And then we have to add those together from x equals 0 to 2. So that's going to be the volume of the purple region, the region that we get from the purple washers. Okay? Then we do the green washers. So we do plus pi times the outer radius, 3 squared, minus the inner radius, x minus 1 squared, times the thickness, which is still dx. We add those together, and we do that from x equals 2 to x equals 4. And now we have our integrals set up. So all that's left is evaluating both integrals and adding the two values together. So let's get that done. All right, so as far as the integration goes, a couple maybe interesting things to look at. Here we're just integrating a constant, which turns into 8x. So I factored the 8 out to the coefficient and then evaluated the x from 0 to 2. No big deal there. Here, I multiplied x minus 1 squared out in my head and then distributed the negative to get this. And then rather than writing a whole other step, because you can see how much there is to write, rather than writing a whole other step to do 9 minus 1 is 8, I knew that in my head, so I integrated each of those terms. Negative x squared gave me this, 2x gave me this, and positive 8 gave me positive 8x. And then I just evaluated the integrals independently from there and then added the results together. Here I got a common denominator and put those together. So that's a great example. We rotated around a line that was not an axis, not the X or Y axis. We had to break the volume into two different pieces because the washers were constructed differently in one region from the other. So there are lots of good things going on here. So as you work through washers, kind of watch for drawing a decent picture. I know that's maybe the hardest part. And then after that, get your inner and outer radii correct. Always measure to your axis of rotation. If you're measuring vertically, it's top minus bottom. If you're measuring horizontally, it's right minus left. So also, it's always pi times your outer radius squared minus your inner radius squared. It can be hard to remember to square those sometimes. Even I forget sometimes when I get in a hurry. So take your time, practice well, do a good job, have some fun.